Hello and good morning everyone. Today inshallah we will continue with the eigenvalues and eigenvectors, and I will hopefully finish today the quadratic part. If something remains, we will try to finish it next week inshallah. So once more we will continue the eigenvalue and eigenvector. It's really a very simple topic we started yesterday, and today is a continuation with some additional remarks, and that's it. It's really a very nice lesson. One of the sessions that's very nice, very easy. You will have to resolve these problems using your app. Of course, all the course materials and everything you will find them on Moodle, and also the recorded lectures you will find them on my YouTube channel. So I think you will be very good if you go through all of this, and please don't forget you will have to use your pen and resolve these problems in order to get the best of these sessions. Today, as I told you, we will continue. So I will start with some exercises from the worksheet of this chapter, just to focus more on the evaluation and to find more problems on the eigenvalue and eigenvectors issue. So here he is giving you three matrices. One of them is 2 by 2, as you can see. The other is 3 by 3, and the other is 4 by 4. He is asking you to find the characteristic polynomial of the real eigenvalues and the eigenvectors of the following matrices. Let's start with the first one. I want you to remember that we started our work by just going through all the main steps of evaluation as mentioned previously. So this is the characteristic polynomial, which is the determinant of a minus alpha in, which is equal to 0. And we already done with this in the previous session. That's the polynomial that if you try to expand it, you will have your characteristic equation, which is very, very simple. This is our matrix. I will go with you as step by step. So for this problem as quick as possible. So let's once more to memorize that this matrix, in order to evaluate the eigen values, all I have to do is to substitute in this characteristic equation. So I will have 1 minus lambda for 1 minus lambda. This is the determinant that's equal to 0, and this is gonna lead to that you will have 1 minus lambda, to the power of 2, then negative 4 equal to 0. All I have to do is to expand this polynomial. So as you know, which implies that I will have lambda squared, negative 2 lambda, then plus 1, and I have negative 4, so the result will be negative 3, and it's equal to 0. Now I can, for this problem, I can factorize it in order to get the spectrum or the eigenvalues, which is really a very simple thing to do. So all I have to do is to factorize this polynomial and putting the result equal to 0. So this is lambda, and that's 3 and 1. The sign is different. So this is negative and that's positive, which will lead to lambda 1 is equal to negative 1, and the lambda 2 is equal to positive 3, as you can see. Now I have the eigenvalues in front of us. Corresponding to each eigenvalue, I will be able to get the corresponding eigenvector for this value. So once more, I get back to the homogeneous system of equations. If you remember, it's just simply A minus lambda I times the unit vector, times the eigenvector that I will need to find is equal to 0. So just substituting in or getting the value of U1, the first eigenvector, which is corresponding to lambda 1, which is equal to, as I told you, positive 1. So now I'm trying to evaluate, negative 1. I'm trying to evaluate the first eigenvector, which is corresponding to the first eigenvalue, which is negative 1. All I have to do, as I told you, is to substitute in this homogeneous system of equations, which means you will have to substitute in this form. So this matrix, it's supposed to be on this form. 1 minus negative 1, that's the first eigenvalue, and those are 4 and 1. Then I will have 1 minus of a negative 1 also, and that's the augmented matrix that we are solving, as you know, which is gonna lead to, I will have 2, 4, 0, and for the second row, it will start with a 2, then 2 and with 1 and 2 and equal to 0. As we mentioned yesterday, you will have to have a relation connecting these rows together, or in another meaning, the rank of this matrix will be less than 2 for sure. So it's obvious, all I have to do is to multiply the first row by negative half and add it on the second row, and then you will have your reduced echelon form, which is gonna be really very easy to find. Dividing on 2, it's gonna be a 1, then it's gonna be 2 equal to 0, 0, 0, and 0. Which means you will have the first component of the first eigenvector, the second component of the first eigenvector, and it's equal to 0. Expanding this equation will lead to u11 plus a 2 over u12 is equal to 0, which means u1 sub 1 is equal to negative 2, hold on, u12 as you can see. Now I have the first vector, which is u1 as we did yesterday, u1 sub 1, u1 sub 2, start to substitute. Okay, so you will have u21, negative 2 u12, and this is u12. So take u12 as a common, as we did yesterday, so it's going to be negative 2 and 1. Consider u12 is equal to 1, so here's your eigenvector, which is negative 2 and 1. That's for the first eigenvector. I can redo the same steps in order also to get the value of the second eigenvector. So this is u2, which actually corresponds to lambda 2 or alpha 2, whatever, which is positive 3. And I will use this value also to substitute in my homogeneous system, exactly like what we did yesterday. So it's gonna be very easy. That's 1 minus 3, and this is 4, 0, and for the second row it will be a 1. Then I will have 1 minus also 3, and it's equal to 0. So all I have to do is to just substitute by the second eigenvalue, which is going to be 1 minus 3, 1 minus 3. I have 4 and 1. So, which simply will lead to, I will have 2 and 4. Then I will have 1, and I will have a negative over 2. Of course, this sign is negative 2, that's 0 and 0. And these are, this is the form after substitution. Also, I will try to get the reduced echelon form, which is once more is very, very simple. Because you will have at least one of the rows is equal to 0, which means the second row is equal to 0. Then reaching the reduced echelon form, you will have a 1, then a negative 2. This is really very simple with Salma. All I have to do is to divide the first row in negative 2. So it's going to be a 1. Then 4 over negative 2 is going to be negative 2 and 0. Then I can multiply in negative and add on the second row, it will vanish. So it's going to be 0, 0, and 0. And once more, now I have the connection between the second vector first component, the second vector second component. Expanded, you will have u2 sub 1 is equal to 2u2 sub 2. And once more, you remember that u2 consists of two components, u2 sub 1 and u2 sub 2. I will make the substitution, which is going to be a 2 of u2 sub 2 and then u2 sub 2. I will take it as a common, u22, which is going to lead to 2 and 1. Then I will consider u2 second component with any number that you would like. Here I don't have fractions, so it's really, really makes sense to take it as 1. So the second eigenvector, it's gonna be a 2 and 1. If you remark, for this symmetric matrix, one of the advantages, and we will read this today through some of the theorems and propositions in the many slides. Once you have a symmetric matrix, you will end up having two orthogonal vectors. How to check if they are, if you have a symmetric matrix. But remark here that this matrix is not symmetric. It's not a symmetric matrix. So I have now two vectors, u1 and u2, which are the eigenvalues, as you can see. If this is a symmetric matrix, as we will see down the road, or like the problems we solved yesterday, you will have these two vectors perpendicular on each other. So if you get the multiplication of them, it's going to equal to 0. Then I will be able to get the also normalize the model matrix, blah, 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 like what we did yesterday. But for this problem, he needs an eigenvalue, an eigenvector, and a characteristic equation. So once more, as you can see, at -1, I will have -2 and 1, exactly like what we did. And with 3, we will have 2 and 1, exactly like what we have in specific, okay? Once more, I will need to solve number B, which is a 3 by 3. But if you give a look for this problem, in specific, you will find the eigenvalues and the eigenvectors. It's very, very simple to evaluate here. Because this matrix, if you look at it, it's not symmetric matrix, but it contains a huge number of zeros. So if I try to evaluate or to get the characteristic equation, it's gonna be very easy. I will have to clean this whiteboard, and let's try the first steps, okay? For these problems, it's a repeated systematic steps. So let's try first to get the eigenvalues. Once more, in order to get the eigenvalues, I will try to subtract minus alpha, so it's a 0 minus alpha from the principal diagonal, 0 minus alpha, and then I will have 0 minus alpha. That's the characteristic equation, which is the determinant of A minus alpha I equal to 0. That's my characteristic equation. So just substituting, you will have 1, then you will have a 0, then this is 1, that's a 0, that's 1, and 0 once more. So, and it's all equal to 0. So if you give a look for this determinant, you will find negative alpha, 1 and 0, then 0, negative alpha and 1, then 1, 0, negative alpha, which is equal to 0. Try to use any appropriate method to evaluate the value of this determinant, either Laplace or Cyrus rule. So Cyrus is going to be really very simple, so I will multiply those numbers. So it's going to come up to negative alpha cube. Then I will multiply 0 times 0 times 0, which is 0. Then plus, okay, 1 times 1 times 1, which is positive 1. Then minus 0. Then minus 0 in the secondary direction. Then another minus 0, which is equal to 0. Now I have a cubic equation. But this equation, you are very lucky, it's alpha cubed minus 1 equal to 0. Of course, they are the same. I've just multiplied in the negative. Since it's equal to 0, it's going to be the same. Now I can factorize this cubic equation in this special case. It's really very simple. So all I have to do is to take alpha minus 1 for the first bracket. For the second bracket, I will start with alpha square. Then since this sign is negative, I will consider a positive sign. This is alpha and that's plus 1. If you try to expand this equation, you will find that it is exactly like alpha cube minus 1. So if I try to expand, alpha times alpha squared is going to be alpha cube. Okay? And I'm using the binomial expansion in order to solve this equation. So alpha times alpha cube, alpha squared is going to be alpha cube. Then alpha times alpha is going to be positive alpha squared. Then alpha times 1, positive alpha. Once more, using the negative 1, it will give you negative alpha squared, so it will eat it. Then negative alpha, it will eat it also. Then you will have negative 1 exactly like that. But the problem is solving this equation will lead to some eigenvalues real, which is alpha is equal to 1, or alpha squared plus alpha plus 1 equal to 0, and this will get complex numbers. So the eigenvalues can be real numbers or complex numbers. We are interested in our course in the real part. So now I have the real eigenvalue, which is alpha is equal to 1, and I can get the corresponding real eigenvector corresponding to 1, which is very, very simple. If you want to continue, I will have to get back to the homogeneous system. Ya tara, do you remember the homogeneous system? How we can solve or to get the homogeneous equation? The homogeneous equation is simply A, if you remember, minus alpha of an I times U, which is the eigenvector, and it's equal to 0. So all I have to do is to solve the corresponding, augmented matrix, which is really very simple. Also, it's gonna be, as you can see, a matrix like this with the alpha elements on the principal diagonal. So it's gonna be 1 minus alpha, so it's a negative 1, negative 1, and negative 1. Then I will have 1 and positive, 1 and 0. Then I will have 0 and the positive 1. Once more, so it's going to be negative 1, 1 and 0, so it's going to be 0, negative 1 and 1. Then it's going to be 1, 0 and the negative 1, as you can see. And that's the system of equations that I need to solve. It's very, very simple. So adding the first row with the last row will give you, I'm trying to get the reduced echelon form, or as close as possible to the reduced echelon form. So just adding the first row with the last row, negative 1 plus 1 is going to be 0. 1 plus 0 is going to be 1. 0 plus negative 1 is going to be negative 1. And here is 0. For the first row, I will multiply in negative. So it's going to be a positive 1, negative 1, 0 and 0. For the second row, also I will multiply in negative. So it's going to be 0, 1, negative 1 and 0. Then remark that the second row and the third row, they are identical. So multiplying in negative and adding, it will eliminate the last row. So now, and I know that it must happen like this, because the rank should be less than 3. So this is zeros. I will have 0, 1 and negative 1 and 0. Then I will need to eliminate this negative 1. So I will add this row to the first row. Alright? Which is 0? ده يعني ما يبوظ. 0 plus 1, 1 plus negative 1, negative 1 plus 0 is gonna be, and it's equal to, is this the reduced echelon form? Yes, this is the reduced echelon form. So, try to expand it once more. This is important. You shouldn't have any hesitation at this time. Once more, the steps. A pivot, all the numbers are zeros. A pivot, above and lower are zeros. Then if you have a pivot, the last pivot will force the elements equal to 0. Please try to stick to the steps. Okay? Now I can get the values. So this is the first vector, first component, the first vector, third component, the first vector, second component. The first row will develop that u1 sub 1 is equal to u1 sub 3, and the second row will give u12 is equal to also u13. So if you make the substitution, this is u1 sub 1, u1 sub 2, u1 sub 3. Start making the substitutions. It will be, this is gonna be u1 sub 3, and this is gonna be u1 sub 3, and this is also u1 sub 3. Consider u1 sub 3 equal to 1 or something. You will have the triple 1, which is the eigenvector corresponding to this value. So once more, as you can see, use the same steps, but see how to factorize the cubic equation that you will have. It's really the characteristic equation is still the same. I want you to remember how we use the binomial. So it's an alpha cube minus 1 is equal to 0. I will stick with the same sign in the first bracket. Then I will replace the sign with the second bracket, as you can see. Now I can find the values. The real eigenvalues equal to 1. The other value is not going to be real. And that's the eigenvector. It's really very simple. But as I told you, for all of you, you will have to resolve these problems more than once. It's not enough just to watch them. Now coming to problem number C, which is in some cases, some of you, once they solve this problem, it will be very difficult for them to continue. But on the other hand, this is really a very simple problem, especially in finding the eigenvalues. If you look to problem number C, you will discover it's a 4 by 4 matrix. Am I right? Yes. But it's a special case. What's the type of this 4 by 4 matrix? It's an upper triangular matrix. The upper triangular matrices have a wonderful property in evaluating their determinants. It's equal to the multiplication of the elements on the principal diagonal. So if you try to evaluate the eigenvalues, it's going to be really, very simple. It's going to be 1 minus alpha, then 3 minus alpha, then 5 minus alpha, then 6 minus alpha. Regardless of whatever here and there, the equation is very, very simple. You will have to multiply them all together. So you will end up having alpha minus 1 times alpha minus 3, alpha minus 5, alpha minus 6 equal to 0. Of course, this is not a cubic equation, it's a typo. It's a fourth degree equation, okay? So it's going to develop that alpha is equal to 1, alpha is equal to 3, and alpha is equal to 5, and alpha is equal to 6. Now I have 4 eigenvalues. Corresponding to each one of them, I will have an eigenvector. If you want to solve it, the augmented system will be exactly similar, but a little bit bigger. But you will have exactly the same steps with everything. So if you want to give it a try with the first one of them, it's very, very simple. All I have to do is to once more solve the system. Please help me out. 1 minus 1, it's going to be a 0. Then you will have 1, 2, and 2. صح? Yes. And this is equal to 0. For the second row, I will have 0, then 3 minus 2, 3 minus 1, it's going to be a 2, then 3, 4, and then 0. For the third row, you will have 5 minus 1, which is going to come up to 4, and then 5, and then zeros, then triple zeros, and you will have 6 minus 1, which is come up to 5, and it's equal to 0. Okay? So the first row was 0, 1, 2, 2, then 2, 3, 4, and so on. I will multiply the second row in negative 2 and add it on the second row. Okay, so if you try to do this, it's very, very simple. If we start substituting, so it's going to be negative 2 plus 2, so the result will be 0. Negative 2 times 2, negative 4 plus 3, so it's going to come up to negative 1. Negative 2 times 2, negative 4 plus 4, so it's going to come up to another 0, which is 0. Which means that's a positive 1. Okay? This is for the second row. Okay, for the first one, it is 0, then 1, then 2, then 2, then 0. Now, I will have to use this one, this pivot, in order to eliminate the 4. So I will multiply negative 4. Yes, you are right. So it's going to be 0, 0, 0. Then negative 4 times 0 is going to be 0. Plus a 5, so it will remain as a 5 and 0. This row, if you multiply it in negative and add it to the last row, you will end up having all of them are zeros. And once more, okay, as you can see, once more, I will have 4 zeros, then this guy is equal to 0, then dividing, so I will have 0, 0, 1, and 0. Then, for the second row, it is 0, 0, 1, 0, and 0. And I will multiply this in negative 2 and add it on the first row. So multiplying the negative 2 and the adding will develop 0. Then you will have 2 and 1. Also, I can multiply this in negative 2, this pivot, and the added on the first row for the second step. And this will lead to, it made complete sense, and this will lead to, that's the first row is 0, 1, double 0, and it's equal to 0. The second row is double zeros, 1 and 0 is equal to 0. The third one is 0, 0, 0, 1 and 0. And the last one is all zeros. Now we get back to our vectors. This is the eigenvector number 1, first component. The eigenvector number 1, second. The eigenvector number 1, third. The eigenvector, and this is the fourth component. Am I right? Okay, so once more, U1 is equal to 4 components. U1 sub 1, U1 sub 2, U1 sub 3, U1 sub 4. Start substituting. So I will have U1 sub 1, but U1 2 from here, U1 2 is equal to 0. U1 3 is equal to, so it's going to be 0, 0, and 0. I will consider U sub 1 is equal to 1, so this is going to be the eigenvector corresponding to alpha is equal to 1. Okay? In a similar manner, I will substitute with 3, 5, and 6, and you will have those eigenvalues, those eigenvectors corresponding to each value of these values. Please try to do it. It will help you out with the fractions and the numbers and the addition. It's really, very important. Okay? For this problem, also it's one of the sheet problems, but since we didn't have the matrix of the transform, but it's really very simple, so I will just give you the matrix that you can use in order to get your eigenvalues of the eigenvector, which is really very simple. Now I have a linear transform. That's transforming, if you remember, x, y, and z, 3 coordinates into R3, from R3 into R3. Those are 3 coordinates and those are 3 coordinates. How the transformation would happen? It would happen using this matrix. If you remark the first component, which is x, am I right? Plus 2y plus 0 and a z. The second component, can you give it to me? The second component?
Yeah, x.
It's a 3 over an x, plus a 2 over y, plus also a 0 in z. And for the last component, can you give it to me?
Negative.
It's going to be 0 in an x, plus 0 in a y, plus z, negative in a z. And this is what's called x, y, and z, which means the matrix will be 1, 2, and 0, first row. 3, 2, and 0, second row. Then 0, 0, negative 1. And this is going to be multiplied in x, y, and z. Then you will have your 4. Fine. If you try to multiply the first row by x, y, and z, you will get the first equation. The second row by x, y, and z, you get the second one. The last one times x, y, and z, you will get the third component. Am I right? Now I can find the eigenvalues and the eigenvectors corresponding to this matrix. So it's really a piece of cake. To determine the required eigenvalues and the eigenvectors, we will have to form the coordinate matrix, which is really very simple. That's the coordinate matrix. Write the components in a complete form. Then try to isolate x, and then y, and then z. So it's going to come up to 1, 3, and 0, exactly as we did, 1, 3, and 0. Then you will have 2, 2, 0. You will have 0, 0, negative 1. That's your matrix. Now I can deal with it normally. I will start subtracting minus lambda from the principal diagonals, okay, in order to get the eigenvalues and solve the equation. The values will be negative 1 with a power of 2 and 4. Those are the eigenvalues if you try to solve this quadratic equation. And it will lead you with negative 1 and these two vectors. I would like to show you how to get the eigen vector here for you and for your companions. So it's very, very simple also in order to evaluate the eigen vectors relative to this equation. By the idea, solving this system or trying to solve the characteristic equation, which is simply A minus alpha I equal to 0, will leave you with alpha plus 1 to the power of 2 after solving and simplifying. Alpha minus 4 is equal to 0. And this will develop lambda 1 and the 2, or alpha 1 and the 2 as the symbols here, equal to negative 1. And the alpha 3 is equal to positive 4. So negative 1 is repeated how many times? 2 times. And the 4, as you can see. So for this matrix, now I know that you will have an algebraic, do you remember the algebraic multiplicity? What's the algebraic multiplicity? The number of repetition of the eigenvalues. Okay, this guy is repeated how many times? 2 times. So the algebraic multiplicity here is 2, and the algebraic multiplicity here is 1. I will try to go with you to find the eigenvectors corresponding to the first element, which is also still really very easy. Use the matrix and help me out. It's gonna be the augmented matrix in order to get U1. It will be 1 minus negative 1. So it's gonna come up to 2. Then I will have 2, 0, and 0. Go for the second row. It's gonna be a 3. Then 2 minus negative 1, it's going to come up to positive 3.
Plus plus?
Yes.
2 minus minus 1?
2 minus negative 1.
Negative 1.
Shinti, the first eigen is eigenvalue is negative 1. So lambda 1, U1 is corresponding to alphas equal to negative 1. So it's going to be a 1 minus negative 1. So it's going to come up to 2. Okay? And this is a 0 and 0. For the last row, please, it's going to be a 0, then 0. Negative 1 minus of a negative 1. So negative 1, okay, plus 1. The result will be? Okay, now I can continue. Okay, I need to reach, as we know, a reduced additional form. So it's really very simple. So once more, I will divide on 2. So it's going to be a 1, 1, 0, and 0. Then I will multiply negative 3 and add. Negative 3 plus 3 is going to be a 0. Negative 3 plus 3 is going to be a 0. Then I will have zeros, as you can see. So from all of this, now I have a relation connecting these values. So this is U1 sub 1, U1 sub 2, U1 sub 3. Now expanding will lead that U1 sub 1 plus U1 sub 2 is equal to, so the first component is equal to negative U1 sub 2. Am I right? Okay, start substituting. This is U1. Consists of how many components? U1 sub 1, U1 sub 2, U1 sub 3. Now start substituting. You will have negative of U1 2. Am I right? U1 2 1.
Negative.
Yes. And this is U1 3, which can be written.
Negative 1, 1.
Am I right? Why I have to do it? Because these two guys are function in the same variable. So it's going to be negative U1 2, U1 2. Do you have U1 2 here? No. So it's going to be a 0. Hey, once more. Do you have U1 3? Do you have U1 3? But here you have U1 3. Am I right? Now take them as commons. You will have the first vector, U1 2, and the shape is negative 1, 1, and 0. Am I right? And for the second vector, which is U1 3, it's going to come up to 0, 0, 1. Am I right? So how many vectors here? So the span, so this is U1. The basis of this eigen space is not one vector. It's how many vectors? 2 of them, negative 1, 1, and 0, and 0, 0, and 1. And in this case, the algebraic multiplicity, the geometric multiplicity is 2.
2. Well, algebraic.
So, the algebraic is 2. Okay, it's not a must, because some problems you will discover that the geometric multiplicity is just only one vector while the algebraic is 2. Okay, but it's a condition for diagonalization down the road. So once more, as I told you, this is for -1. Those are your 2 vectors. Similar steps exactly, but replacing alpha by 4, you will get the value of your last eigenvector. Any questions? Okay, very good. Now I will get back to our slides once more. So most of the slides are covered, but we will need to go through them to strengthen our information and to state the propositions and theories as they are stated in the main slides exactly. So now we know every detail, combining the examples that we had in the previous lecture and with the couple of examples that we had today, we completed the lecture regarding eigenvalue and eigenvector. So by the look, when he gives you something like this and he asks you to find the corresponding eigenvalues and eigenvectors, it's going to be really very simple. When I look to this matrix, it's a piece of cake because it's an upper triangular matrix, so the evaluation of the eigenvalue is going to be really, really simple. It's going to be 2 minus alpha, 2 minus alpha, 1 minus alpha. So once you try to evaluate, you will have lambda minus 2 to the power of 2 times lambda minus 1. So now the values will be lambdas equal to 2, and it is repeated 2 times. The algebraic multiplicity is 2. And here lambdas equal to 1, and the algebraic multiplicity is equal to 1. So very simple, lambdas 2 with algebraic multiplicity is equal to 2. And the lambda is equal to 1. If I try to get the eigenvalues corresponding to 1, all I have to do is to solve the homogeneous system as we trained, and put it on the reduced echelon form. You will get your relation and you will find your eigenvectors. In a similar manner, for lambdas equal to 2, I will do the substitution. Okay, I will do the substitution.